Okay, so welcome everyone to today's Gantt seminar. Our speaker today is Christos Tatakis from the University of Western Macedonia, and he's going to give a talk about toric ideals of graphs minimally generated by Grobner basis.
Okay, I would like also to thank all of you for the invitation also. Today I will talk about a special class of toric ideals of graphs, and we will discuss about ideals which are minimally generated by a Grobner basis. First of all, this is a joint work with Ignacio Garcia Marco and Irene Marquez Corbella. Both of them are professors in the Department of Mathematics in Tenerife, University of La Laguna, Canary Islands. This is our last work. We submitted it this month. We will see today, we will do an introduction to the main toric basis of a toric ideal, okay? And then we will discuss about the two main properties that they have, robustness and generalized robustness. We will see what means, and then we will see our problem. Okay. So, okay, the basic definitions. What is a toric ideal? We have a vector configuration. A1 up to AM are vectors, and we grade the polynomial ring kx1 up to xm over a field k by setting the a degree of each variable xi is equal to ai. Okay, if we have a vector u in um, then we define the usual a degree of the monomial xu as the sum that you can see. Okay, while the usual degree of the monomial is defined as the sum of its powers. So the toric ideal is the binomial and prime for sure ideal xu minus xv such that the a degree of xu is equal to the a degree of xv. For each set of vectors A, we have the corresponding toric ideal. Okay, some very important papers and in this topic. Toric ideal started from Hodgster, but the main the main when toric ideals became popular were by Fulton in a series of lectures. The following three papers are very important. The first one by Sims, Vasconcelos, and Villarreal. They introduced toric ideals in graph theory, and they introduced the toric ideals of graphs. Eisenbach and Stumpfels in their paper gave a lot of known results now about binomial ideals, and Diakonis and Stumpfels in this paper did the connection between the toric ideals and the Markov basis. Okay, what is a toric ideal of a graph? So we have just to define how we want to just to see how we define the A set. Okay, so now our polynomial ring, its variables are the edges of the graph. We have a finite simple connected graph over a vertex set and over an edge set. We take the polynomial ring with variables the edges of the graph, and we will associate each edge of the graph with the element AE, such that the AE is the sum of Vi and Vj. So what is AE? Is a vector with two ones in the I and j position, and all the others are zero. Okay, if we take all these vectors, we have the AG set. So we denote by IG the corresponding toric ideal. For example, in this graph, we can see a graph with 12 edges. So we are in a polynomial ring within 12 variables. It's easy to see that the corresponding toric ideal consists of the following 10 elements. So why we will see why we study this class of toric ideals. So Villarreal back to 1995 gave us a better description of the toric ideal of a graph G. He proved that the toric ideal of a graph G is generated by binomials of the form BW such that W is an even closed walk of G. So if you want to describe a toric ideal of a graph G, you have just to see all its even closed walks, and then you just take the corresponding binomials. Toric ideals of graphs started to studying in 1995 by Sims Vasconcelos Villarreal, and then with a lot of papers by Hibi, Ohsugi, Stumpfels, Katzmann, and a lot of others. An example, here is a very simple example. We have just two squares, 8 edges, the graph, so 8 variables in the polynomial ring. By Villarreal's theorem, we have 3 even closed walks, W1, W2, and W3. Each of them gives the corresponding binomial which belongs to the toric ideal. Okay. So if someone see more, okay, we will see next. No. Okay, sorry.
Can I ask something? Maybe I missed it. You
Yes.
said, how do we decide the signs, the minus there?
It doesn't matter. Just if you start with E3, for example, you just want to take even closed walks. Okay.
Okay.
So just find here the even closed walks.
Maybe okay. So they swap each time you go from an edge to the other, maybe.
Yes.
Okay.
So the corresponding binomial is the same. Just maybe they differ by a sign, but we don't care about the sign because they are minimal generators.
Okay, thank you.
Okay. So we will see some what we called toric bases. They are very important sets which describe absolutely the toric ideal of a graph. First of all, the Gröbner basis. The Gröbner basis consists of primitive elements. What is primitive binomial? An induced binomial is called primitive if there is no other binomial xw minus xz such that xw divides xu and xz divides xv. The set of all the primitive binomials forms the Gröbner basis of the ideal. In the previous example here, you can see that, for example, BW3 is not primitive because of the existence of BW2. Okay, E3, E5 divides E1 and E5 is 7, and E4, E6 divides E2, E4, E6, E8. So BW3 is not primitive. It does not belong to the Gröbner basis, while BW1 and BW2 are primitive elements. The importance of the Gröbner basis, first of all, it's a set of generators of the ideal. It includes at least one minimal set of generators. If the corresponding affine semigroup NA is pointed, then every minimal generator of the ideal belongs to its Gröbner basis. Every reduced Gröbner basis is a subset of the Gröbner basis. Also, the universal Gröbner basis of the ideal is a subset of the Gröbner basis. And also, the set of the circuits of the ideal is a subset of the Gröbner basis. So, if NA is pointed, all the Toric bases are subsets of the Gröbner basis. Markov basis. A set of Markov bases are the minimal system of generators of the ideal. A set of generators is minimal if there is no other set of generators such that it includes in the first one. A generator of the ideal is called minimal if it belongs in at least one minimal set of generators. For example, in the previous example, it's easy to see someone that BW3 is not minimal here because it is a linear combination of BW1 and BW2. Okay, here is the combination. So BW1, BW2, and the BW3 is a set of generators of the ideal, but not minimal. The BW1 and BW2 is a minimal system of generators. By Jacobs and Stoffels, a minimal generating set of the ideal is called a Markov basis, and we denote it by MA. What we call the universal Markov basis, the union of all the Markov bases of the ideal, and is proved that it is a finite set. In the previous example, we saw that the ideal can minimally generated by these two binomials, but it's very easy to see that the ideal has exactly one Markov basis, so it follows that the universal Markov basis is equal to this Markov basis. The set of the circuits, okay, I just refer here the definition, but we don't use it in our paper, just for the completeness of the talk. The set of the circuits are just consists of the reducible non-zero binomials which has minimal support. Okay, for example, in the previous example, BW3 is not a circuit since its support has these 8 elements, while BW1, its support is a subset of the support of BW3. Okay, our main topic here is the universal Gröbner basis. The universal Gröbner basis, okay, it is known, is defined as the union of all reduced Gröbner bases of the ideal. Is a finite subset of the ideal and is a Gröbner basis for the ideal with respect to all admissible termoides. We denote it by UA. In the previous example, easily we compute that the universal Gröbner basis of the ideal is again the set BW1 and BW2. The Loera-Stumpfel set Reka Thomas in 1995. I just write it here just to see the situation, how complicated it is when n increases. Kn is the complete graph over n vertices. So for the complete graph up to 7 vertices, the set of the circuits, the number of the elements of the set of the circuits is equal to the number of the elements of the universal Gröbner basis equal to the number of the elements of the Gröbner basis. You can see here that they also compute that, have a look, these numbers when n increases for K5, 30, K6, and so on, okay? Now, why we study Toric ideals of graphs? Because we have a complete description for all these bases. And okay, to the best of my knowledge, I think it's the only family of toric ideals that we know exactly all these sets. And that's the reason. The set of the secrets, we know it by Villarreal. Also, 1995, the universal Grobner basis, we know it in 2011. Also, the sets of the minimal Markov basis, the universal Markov basis. SA, we denote by SA the set of the dispersal binomials in a minimal generating set. And also, it's known the Grave basis of the ideal. In the previous example, I just argue here the relation between all these sets. Okay, it's very important example for us. That's why I have it a lot of times. So by Stumfers, we know that the set of the secrets is a subset of the universal Grobner basis, which is a subset of the Grave basis. By Haralambous, Thoma, and Bladoriu, we know that if the NA is pointed semigroup, then every minimal generator of the ideal is an element on the Grave basis of the ideal, okay, the universal Markov basis. And very useful for our proofs property. For toric ideals of graphs, we know that every minimal generator of the ideal is an element of the universal Grobner basis of the ideal. But this holds only for toric ideals of graphs. Now, some important classes of ideals, well known. A toric ideal, first of all, is called robust if its universal Grobner basis is a minimal set of generators. Okay, while we call it generalized robust if its universal Grobner basis equals its universal Markov basis. And by Sullivan, we know that an ideal is called strongly robust if its Grave basis is equal with its set of indispensable binomials. Okay, we don't care about strongly robust. The reason is that in the case of toric ideals of graphs, robustness and strongly robustness are the same. That's why. Now, quadratic toric ideals. A toric ideal is called quadratic if it is generated by quadrics. Okay, all its minimal generators are of degree 2. In our previous example, the corresponding ideal is quadratic. Okay. Previous results and about robustness, generalized robustness about this toric basis, and our interest. Let show you robustness. Okay, about previous results, Bucher et al. I think 5-6 guys studying robustness for toric ideals of graphs, and they gave necessary and sufficient characterization of robust toric ideals of graphs. But in terms of graph restrictions of the secrets of the graphs. Okay, and they also proved that the toric ideal of a graph is robust if and only if the Grave basis is a minimal set of generators. Also, the corresponding theorems proved for the generalized robustness property for toric ideals of graphs. Previous result which connect robustness and quadrics. First of all, Ohsugi and Hibi characterize completely the graphs whose toric ideals are generated by quadrics. Bucher and Rebeva studying also robustness for toric ideals which are generated by quadrics. And in the other paper, Bucher et al. Studying robustness for toric ideals of graphs which are generated by quadrics. Moreover, they proved that all robust ideals generated by quadrics are graph ideals, okay, and come from the family of disjoint unions of graphs given in the following figure. Okay, not this figure because it was it had crucial information for us. the interest. Why we care about robustness and quadratics? First of all, okay, White's conjecture. The toric ideal for a materoid is generated by quadratics. Ohsugi and Hibi asked when the toric ideal has a Grobner basis, which consists of quadratics. I remind you the connection between robustness and generalized robustness and Grobner basis. Okay. Some of the interest in studying robustness stems from the fact that they are ideals which are minimally generated by a Grobner basis. If you connect this, we have that one common strategy for proving that the question ring is a causal algebra involves showing that the ideal is an MG ideal. We will see what is an MG ideal generated by quadratics. Okay. Now, let me, yes. So we, in a previous paper with Nacho, with Ignacio Garcia Marco, we gave sufficient and necessary characterization about toric ideals of graphs which are generalized robust and also robust in another theory, and is generated by quadratics. Okay, in graph theoretical terms. So we have this theorem that the ideal is generalized robust and is generated by quadratics if and only if all the blocks of the graph are bipartite except one, which has one of these forms. Just look the figure. Okay, it's technical definition. The non-bipartite block it can be the K4, the complete graph of 4 vertices, or look here we have the figure of Bucher, but we add an edge in these 2 vertices, or in these 2 vertices the same. Or the non-bipartite block can be a graph of what we call double K2NM, okay, technical definitions, or a graph of this form. And also we gave if and only if about robustness, when a toric ideal is robust and is generated by quadratics. Again, the only difference is that the non-bipartite block can be one of them except K4. It's the only difference. For example, look here in the figure 1, a graph G here. The corresponding toric ideal is generalized robust because of the theorem and is generated by quadratics, but it is not robust. The reason is the existence of K4, okay, the last block. In figure 2, we can see a graph such that the corresponding toric ideal is both robust, generalized robust, also strongly robust, and is generated by quadratics. Another example, just the K4, okay? If someone wants to check if the corresponding toric ideal is robust or generalized robust, has to compute the ideal, okay? It has these 3 elements. None of them is indispensable. It's very easy to check it. The ideal has 3 different Markov bases, M1, M2, M3. The universal Markov basis is union, so consists of these 3 elements. It is easy to check that the universal Grobner basis has also these 3 elements, and it follows that this quadratic ideal is generalized robust but not robust. By our theory, immediately, without computations, because of the existence of K4, is not robust and generated by quadratics, but is generalized robust and generated by quadratics. And just the K4, okay? Not a very, it's a simple graph. So the ideal is very simple. Now, I will introduce you in our problem. We introduced the notion of MG and the notion of UMG ideal. An ideal is called an MG ideal if it is minimally generated by a reduced Grobner basis of the ideal for some monomial order. Okay, while the ideal is called a universal MG ideal, if every reduced Grobner basis of the ideal is a minimal set of generators. For example, here we have this graph. The corresponding Toric ideal consists of the following 10 elements. With Sage Math, computer system program, the reduced Grobner basis have at least 12 elements. And so one has that there is no monomial order such that the ideal is minimally generated by a Grobner basis. Okay, so the Toric ideal of this graph is not UMG-graph. While, look now, if I just add an edge here, we have an ideal which is an MG ideal. The corresponding Toric ideal is minimally generated by these 13 binomials, but now, with Sage Math again, we can see that the Toric ideal has many reduced Grobner bases that coincide with the Markov basis of the ideal. These two exams make us to search a lot to understand why just the edge make the difference, the reason. Okay, it was we did a lot of exams to understand why this edge make the difference for us. And our motivation for our paper was the following theorem by Ohsugi and Hibi in 1999. They proved that if we have a bipartite graph means is a graph which has no odd cycles. So if we have a bipartite graph such that the corresponding ideal is generated by quadrics, then the ideal is an MG ideal. Our problem, try to generalize the above result. Okay. Actually, the true story of our paper was that independent of Ohsugi and Hibi, we didn't know their result. And with Nacho and Irene, we proved their result with a completely different way. But when we started to write it, we found it in internet, and then okay, our theorem completely destroyed, and we just then we thought how to generalize the above result. So if we look here, we have a Toric ideal which is generated by quadrics. So what happens if the Toric ideal is generated by quadrics means all its generators have a degree 2. Okay, if all of them have degree 3 or 4 or 5 or 6, okay, and then we try to generalize this result. Previous results by Delora, Stumfels, and Thomas, they proved that Toric ideals of complete graphs are MG graphs, MG ideals, okay. Ohsugi and Hibi proved that the Toric ideal of a bipartite graph, which is generated by quadrics, is an MG ideal. Okay. In general, it's a difficult and computational demanding problem due to the fact that one has, as I told you, to know explicitly all of the Toric bases of the ideal. Okay. Results. In general, UMG ideals and generalized robust ideals are distinct. If we can see here in the following example, we can see a Toric ideal, not for graphs. Okay, here we have a numerical semigroup. The corresponding Toric ideal consists a minimal system of generators consists of two elements, either F and G or F H or F and P. But every reduced Grobner basis is is either Fg or Fh. This ideal, so, is a UMG ideal, but it's easy to check that P does not belong to the universal Grobner basis of the ideal, and so the ideal is not generalized robust. But first of all, we proved that this is true for toric ideals of graphs. If we have a graph G, okay, the corresponding toric ideal is an UMG ideal if and only if the ideal is generalized robust. In the general case, this does not hold, as we saw, but in the case of graphs, it holds. This theorem gave us the following corollary. In the case of bipartite graphs, the following are equivalent. G is choiceless. Choiceless means that its cycles are primitive. They have no codes. The corresponding ideal is robust if and only if the corresponding toric ideal is a UMG ideal, if and only if the corresponding toric ideal is generalized robust. And after this, it was easy to prove to give a big family of MG ideals. If we have a bipartite graph and the corresponding toric ideal such that the corresponding toric ideal is a complete intersection toric ideal, then this ideal is an MG ideal. Now, answering our problem, I remind you the problem. The problem was to generalize the result of Hibi and Ohsugi. I remind you the theorem. We have a bipartite graph such that the toric ideal is generated by quadrics. Then the ideal is an MG ideal. These results helped us to prove an extension of the theorem. Our theorem is if we have a bipartite graph such that all minimal generators of the corresponding toric ideal have the same degree. Then the ideal is an MG ideal. Hibi and Ohsugi proved for degree 2. For us, for any degree. And the above theorem does not hold in the case of non-bipartite graphs. Here we have the counterexample. We can see that here we have, first of all, a non-bipartite graph. Okay, we have cycles, for example, of length 3 inside. The following graph, the corresponding toric ideal of the following graph, is generated by quadrics. All its minimal generators have the same degree. Okay, it's easy with sage math to check that every Grobner basis of the ideal has at least 9 elements. Which means that the graph is not an MG graph. So the theorem does not hold in the case of non-bipartite graphs. But when G is bipartite, we have that all minimal generators of the corresponding toric ideal have the same degree, if and only if all ordered cycles have the same length. If G is non-bipartite, then the previous equivalence is no longer true. And this remark suggests two ways of trying to extend our theorem for non-bipartite graphs. First case, if all ordered cycles of G have the same length, then G is an MG graph, an extension, or if all the generators of the ideal have the same degree, then G is an MG graph. Okay? For B, we show the counterexample, okay? Sorry, for A, I showed you the counterexample. For B, Hibi and Ohsugi gave a counterexample. And here, so there is no extension more in our theorem, while the existence of these two counterexamples. And also, if you look here, the figure, the first figure, we can see a graph such that the corresponding toric ideal is minimally generated by 8 quadrics and 1 cubic. The cubic is the cycle of length 6, the outside cycle of length 6. Okay. Now, what next? Next, someone can search about to give complete characterizations of the graphs such that the toric ideal is a generalized robust toric ideal. We gave a complete characterization, but only in the case of generalized robust toric ideals, which are minimally generated by generators of degree 2. We have if and only if, but only in this case. Also, a very interesting problem is to give a complete characterization of the graphs such that the corresponding toric ideal is a robust toric ideals. Okay, another interesting for sure problem is find bigger families of bipartite or not, MG or UMG graphs. Okay, we gave, for example, complete dissection toric ideals are a very interesting family of MG ideals, of bipartite graphs, and also our theorems, but can you extend this? And other two problems, not in the case of toric ideals of graphs, very distinct problems. First, if the ideal is robust, is the ideal minimally generated by its Gröver basis? It's open problem, last 10 years. I think it's not very easy to prove it. I have no idea. I tried, but I didn't achieve it. Equivalent with this problem, a similar one, if the ideal is generalized robust toric ideal, does it hold that the universal Grobner basis is equal to the Gröver basis of the ideal? Also, another interesting problem. If someone answers one of them, then immediately has the answer for the other one. Okay. Okay. Thank you for your attention.